Have you ever just looked at your phone and wondered how on earth does it know that's my face? Or how can a car see a stop sign? Well, it all boils down to teaching a machine how to see. And today, that's exactly what we're going to do. We're going to build a simple AI right from scratch to figure it all out.
I mean, think about it. For us, it's easy, right? We see an apple, we know it's an apple. But for a computer, a picture is just a giant grid of numbers. That's it. So how do we bridge that gap? How do you go from a bunch of numbers to the idea of an apple? That is the central puzzle we're going to solve together.
And to do that, we're setting ourselves a mission. We are going to build an AI that can look at a picture and tell us if it's an apple, a banana, or a cherry. And believe me, by the time we're done here, you'll get exactly how this whole thing works.
Okay, but before we can build our fancy fruit spotting AI, we've got to get familiar with the tools of the trade. Think of these as the absolute basic building blocks, kind of like the logic gates that make all of modern computing possible.
So, first thing you need to know is there are two main ways to go about this. In supervised learning, we act like a teacher. We show the AI a ton of examples that are already labeled, like this is an apple, this is a banana. But with unsupervised learning, we just dump a bunch of data on it with no labels and say, hey, go find some interesting patterns in there for us.
All right, our first tool is the Support Vector Machine, or SVM for short. Its main job is classification, basically sorting data into different groups. It does this by drawing the best possible line to separate them. And now, what makes an SVM so clever is that it doesn't just draw any line. It finds the line that creates the biggest possible buffer zone, the widest cushion on either side. This makes the model way more confident and less likely to mess up when it sees new data for the first time.
Next up, we've got linear regression. Now, if SVMs are for sorting things into boxes, regression is for predicting a specific number. You know, like figuring out a house price based on its square footage or what the temperature might be tomorrow. It works by fitting the best possible straight line through the data points to model that relationship.
And finally, from the unsupervised world, we have k-means clustering. With this one, we don't give it any labels. We just say, hey, I think there are about 3 groups in this data. Go find them. The algorithm then figures out the best way to group all the data points around k different center points. It's an amazing way to discover hidden structures you never knew were there.
So, quick recap of our toolkit. We've got SVM for classifying things, linear regression for predicting numbers, and k-means for finding hidden groups. 3 totally different tools for 3 very different but super important jobs.
Now those tools are great, they're powerful. But for something as messy and complex as recognizing images, we need to upgrade our engine. We need something that can think a bit more like a brain. It's time to talk about neural networks.
See, the problem is a simple straight line just won't cut it. The patterns of pixels that scream apple are way too complex. They're what we call nonlinear. They twist and turn. This is where our basic toolkit starts to struggle, and it's exactly where neural networks shine.
And at the very core of this digital brain is the artificial neuron. Just think of it as a tiny little decision maker. It takes in a bunch of signals, or inputs, decides how important each one is, that's the weight, and then based on all that, it decides whether to fire off its own signal. It's a simple little switch, really, but when you connect millions of them together, that's when you get something truly powerful.
And that's the beauty of it. One neuron on its own isn't a genius, but when you start stacking them up in layers, an input layer to receive the data, 1 or more hidden layers in the middle, and an output layer to give the final answer, you get what's called a multi-layer perceptron, or MLP. And those hidden layers, that's where the magic happens. That's where the network learns to see all those complex, abstract patterns we were talking about.
Okay, so we've got our powerful engine. Now we need to give it the right kind of fuel. And for a neural network dealing with images, that fuel, the data, has to be prepared in a very, very specific way. This is probably the most important part to get. A neural network is completely blind. It can't see a picture of a cherry. It can only process numbers. So our entire job at this stage is to translate our images into a numerical language that the network can actually work with.
So a regular color pixel has 3 numbers, 1 for red, 1 for green, and 1 for blue. To make life easier for our AI, we often just convert the image to grayscale. This simplifies every pixel down to just a single number representing its brightness. Yeah, we lose the color information, but we keep the shapes, the edges, and the textures, which is usually all the AI needs anyway.
So this brings us to our full image pre-processing pipeline. It's a 4-step recipe. First, we resize all the images so they're the same size. Second, we convert them to grayscale. Third, we scale the pixel brightness values so they're all neatly between 0 and 1. And finally, we take that 2D grid of pixels and we flatten it into one long, single line of numbers. Now, our fuel is finally ready for the engine.
All right, this is it. We've got our toolkit of concepts. We have built our neural network engine. We've prepared our fuel. It is time to start the assembly line and put this all together to see our AI come to life.
So here's the entire game plan, from start to finish. We start by loading our big data set of fruit images. Then, we run every single one of those images through that pre-processing pipeline we just designed. After that, we split our data. We use most of it to train the model, but we hold back a small chunk to test it later. And finally, we'll see how well it performs on that test data that it has never ever seen before.
And that brings us to the moment of truth. You know, it's one thing for an AI to memorize the answers from its training data. The real test is whether it can generalize what it's learned to brand new images. Can it actually see? Let's find out.
And the results are in. It's incredibly accurate. That means our AI correctly identified the right fruit in new pictures almost every single time. That is a fantastic result for our little digital brain.
But we can dig even deeper than just the overall score. This report here shows us things like precision and recall for each type of fruit. And what this tells us is that our model isn't just getting the easy ones right. It's performing really well across the board, for apples, for bananas, and for cherries. It actually learned the unique features of each one. So there you have it. We did it. We started with some basic machine learning tools. We built a powerful neural network engine. We prepped our images like high-quality fuel, and we put it all together to build an AI that can genuinely see and classify different kinds of fruit. We've successfully taught a machine to tell an apple from a banana. But you know what? The exact same principles we use today can be scaled up to recognize cats, cars, cancerous cells in medical scans, you name it. The fundamentals are the same. So the only real question left is, what should we teach it to see next?